Today we are going to discuss a very important fact regarding the wave motion. In fact, a mechanical wave in a fluid. When you say fluid, that means either liquid or gas, is have actually two representations. One is called displacement representation of the wave and another is called pressure representation. It means a longitudinal mechanical wave in a fluid may be described in terms of the longitudinal displacement suffered by the particles of the medium or in terms of the excess pressure generated due to the compression and rarefaction. When you actually describe the wave in terms of the longitudinal displacement suffered by the particles of the medium, then you call such a wave as displacement wave. And when you describe the wave in terms of the excess pressure generated due to compression and rarefaction, then such a wave is called pressure wave. So the same longitudinal mechanical wave in a fluid has actually two representations. But there is something different in these two representations. So in this lecture, we will see which representation for the mechanical longitudinal wave is the most appropriate or superior. Okay. In fact, a common example of longitudinal mechanical wave in a fluid is sound wave. When sound wave travels in air, then it is a longitudinal wave, and this sound wave may be described either in terms of the displacement suffered by the particles of the air or in terms of the excess pressure, or that is change in pressure developed in the medium. But which representation will be more appropriate in case of sound wave? You will learn in the last of the lecture that the pressure representation for sound wave is the more appropriate representation. Okay. But why the pressure representation is more appropriate, we will learn. In fact, in my previous video on a stationary wave, while discussing the important facts regarding the stationary wave, I have told you that a stationary wave may be a transverse wave. For example, the stationary wave produced on a stressed string by the reflected wave, that is transverse nature. But when you talk about the stationary wave in a liquid or in a gas, then it is of longitudinal nature. Okay. And I have told you that the longitudinal wave, stationary wave, may be represented either in terms of pressure variation or in terms of displacement of the particle of the medium. So that fact here we will explain in very detail. Okay. And for this, now you can see as the longitudinal mechanical wave has two descriptions. It may be treated like a displacement wave or a pressure wave. So when you consider that psi of xt is the displacement of the particle of the medium, then it is called displacement wave. In this condition, this displacement psi of xt acts like the wave function. This is the wave function for describing such a wave. On the other hand, as due to compression and rarefaction, pressure of the medium gets changed and excess pressure or change in pressure is developed. So that excess pressure, if you denote by the symbol P, that will be also a function of a space and time, and that will act like a wave function in this case. So you can say that actually the longitudinal mechanical wave can be described in terms of two types of wave functions. First wave function will be the displacement psi of the particles of the medium, and another is the excess pressure developed in the medium. Okay. How actually these two descriptions are related to one another, and which description is more appropriate, we will see in this lecture. Okay. And for this, let us consider that a longitudinal mechanical wave is moving through a medium, and that medium must be a liquid or a gas, or you can say that a fluid. And we consider that this mechanical wave is going in x direction. Okay. And here, for simplicity, I have considered the medium as a cylindrical column. Okay. And let us see, relative to some arbitrary origin, I have considered a section A here of the medium, which is at x equal to x. It means the x coordinate of this section A is x. And when the wave passes through this medium, then this section or the particle at this section gets displaced by the amount psi, as you can see in this figure. It means this A is displaced to the position A prime, which I have shown by this dotted line. Okay. Then if the particle suffers a displacement psi, then such a wave can be represented by the equation psi of xt is equal to A sine omega t minus kx. This is just equation of a plane progressive wave. Okay. So I have mentioned it here. You can see that the wave going in x direction in the fluid we have considered. And suppose at time t, the particle at the undisturbed position x suffers a displacement psi in x direction. And so the displacement of the displacement wave then will be described by this equation psi of xt equal to this much. Okay. Now consider a cylindrical column of the medium lying between x equal to x and x equal to x plus delta x. That is, we consider that AB is a cylindrical column of the medium in undisturbed condition. So in undisturbed condition, you can say that the length of this column is delta x. When undisturbed condition or undisturbed state means what? When wave is not passed through it, then the length of this column is delta x, and it lies between x and x plus delta x. Now when the wave passes through it, the medium gets disturbed, and this section A is displaced to A prime. That is, the particles of the medium at A or at x equal to x is displaced by psi. Okay. And the particles of the medium at this section B, that is at x equal to x plus delta x, now is displaced to the position B dashed by the amount psi plus delta psi. It means I have considered here that the displacement of this section B is greater than that of A by the amount delta psi. We have considered it. Okay. Actually, due to this change in length of the column, there will be a change in volume of this element. Okay. And change in volume means a bulk strain will develop in the medium. But a strain is always caused by a stress. So definitely a stress has been developed. When you say bulk stress, that means excess pressure. So definitely after passing the wave through this medium, the pressure of the medium does not remain at its normal value, but it will get changed. And that change in pressure is called excess pressure, and that is in fact the bulk stress. So our aim is to now find what will be that bulk stress, finding the bulk strain. In fact, this problem I have already dealt earlier while providing the video on continuous media. And I have followed there a rigorous method to find the volumetric strain. And you have seen that we have used Taylor's expansion for finding this. You have already learned this. Again, here we can follow the same process, but I am not following that because you have already learned. Here, our prime aim is to discuss the behavior of the displacement and pressure wave. So I am following a very simple method here, very simple, not a rigorous method, for finding the volumetric strain and corresponding stress. Okay. You can easily see that the displacement of the section at x equal to x is psi, and that at x equal to x plus delta x is psi plus delta psi. Okay. So, but in undisturbed state, the length of this element was delta x, and if you consider that the area of cross section of this cylindrical column is S, then what will be the original volume of the element? That will be simply area of cross section S times delta x. So you can see I have calculated here. I have mentioned that consider the element of the medium which is confined within x and x plus delta x in undisturbed state. Okay, and if S is the area of cross section, the volume of the element in undisturbed state will be this much, V equal to S delta x. But as I have told you, as the wave passes, the ends at x and x plus delta x are displaced by psi and psi plus delta psi respectively. So what will be the increase in volume? When actually we will multiply the area of cross section by increase in displacement, then we will get the increase in volume. This is an elementary method. This was actually found by Taylor's expansion in my previous video. That was a rigorous method. But here I am following a very simple technique. So change in volume or increment of volume of the element is S times delta psi. And in this equation 2, you have defined the original volume, that is the volume of the element in undisturbed state when no wave was passed through it. That was S times delta x. Now you know, if we will divide this increase in volume by the original volume V, then we will get actually the volumetric strain. So the strain or volume strain developed in this medium is given by delta V over V. But you have calculated that delta V is S times delta psi, and original volume V is S times delta x. Now this S and S will cancel out, and so this volume strain is simply delta psi by delta x. Now if you consider that the element is infinitesimally small and the displacement suffered by the sections A and B are also infinitesimally small, in that condition we can write this equation in this differential form. Instead of delta V, we can write dV. Okay, and instead of delta psi by delta x, you can write del psi by del x. Here I have not written d psi by dx. Why? Can you say? Because psi is a function of two independent variables, x and t. So if you want to find the change in psi with respect to x, then you must take t constant, and so you must take the partial derivative. So the volume strain developed in this medium dV by V is defined as del psi by del x, and this is a well-known expression. I have taught you this fact earlier several times. So uh, if you wish, you can write this expression directly, because you know that volume strain developed is simply del psi by del x. Okay. Now, you know, if B is the bulk modulus of elasticity of this medium, then how this B is defined? This is defined as bulk stress divided by bulk strain. But you know, if you assume that this small p represents the excess pressure, that excess pressure is actually the measure of bulk stress. So at the place of bulk stress, I have written here P, a small p, which represents the change in pressure or excess pressure. And this dV by V, you know, this is the bulk strain. And we put here minus sign. I have already talked about this minus sign, why we put it, because you know, whenever pressure increases, volume decreases. Okay. So corresponding to the positive value of P, definitely dV will have negative value. So this minus sign simply indicates that with increase in P, that is increase in pressure, there is a decrease in volume. So we always put here minus sign in the definition of this bulk modulus. And that's why, as this strain is created here, but you know, from the theory of elasticity, a strain always corresponds to a stress. A stress is the cause of a strain. Always a stress produces a strain. So this bulk strain has been created definitely by some bulk stress, and that bulk stress is this small p. So corresponding stress, which is actually the excess pressure developed in this element at position x at time t, will be what? You can see this result. We will take the cross multiplication. P will be equal to B times minus dV by V, or dV by V, you have seen that this is del psi by del x. So the bulk stress developed in this element at position x at time t is given by P equal to minus B times del psi by del x. Okay. B is here bulk modulus. You may also write the symbol E for this elasticity. Okay. Now, if your aim is to find this excess pressure P, you must find the value of this del psi by del x. This is gradient actually. And how we can find it? As you have already defined in equation 1, psi as a function of x and t in this manner, psi equal to a times sine omega t minus kx. You know, here a is the maximum value of psi, which is called amplitude of the wave. And from this result, you can see del psi by del x, this will be equal to minus ak times cosine of omega t minus kx. So now let us substitute this value of del psi by del x in this equation 5 for getting the value of excess pressure. Okay. So the excess pressure, you can see, will be equal to this much, akb times cosine of omega t minus kx. Now, instead of a times k times b, I have written here p naught. Actually, this represents the maximum value of this p. Okay. So I have mentioned it here. P naught is equal to akb. Actually, this equation 6, you can write this equation in this manner. P of xt. P is also a function of space and time. And this is equal to P naught cosine of omega t minus kx. Okay. Actually, here this p of xt is the wave function which describes this wave, and so that this equation represents the pressure wave. Wave is not different, wave is same, but at first we have described that wave in terms of the displacement suffered by the particles of the medium. Now we are describing the same wave in terms of the excess pressure developed in the medium. Wave is not different, but this wave has two representation. First one is the pressure, first one is displacement representation, and this is its pressure representation. Okay. So I have mentioned it here. You can see that equation 6 represents the pressure wave, when 1 represents the displacement wave. Okay. When you will write the displacement wave equation in terms of sine function, then you will have the pressure representation of the wave in terms of the cosine function. Okay. So it is clear that this wave can be described either taking the displacement suffered by the particle of the medium as a wave function, or the excess pressure developed in the medium as a wave function. Okay. So there are there may be two wave functions to describe the same wave. Okay. Now after getting this result, let us see some of the important facts regarding this. Okay. As I have told you several times, I have mentioned it here, the same thing. A longitudinal wave in a fluid, for example sound wave in air, may be considered as either a displacement wave described by the equation psi of xt equal to a sine omega t minus kx, or as a pressure wave described by the equation p of xt equal to p naught cosine of omega t minus kx. So it is now very clear to you that this, if you are talking about a longitudinal wave in a fluid, for example sound wave traveling in air, then you may represent that sound wave either in terms of this displacement equation or in terms of this pressure equation. Okay, these are the two representation of that sound wave. Okay, but see, the displacement representation of the longitudinal wave is in terms of the sine function, and the pressure representation is in terms of the cosine function. And you know, if you are talking about the two functions sine theta and cos theta, let us see, when theta is equal to 0, sine theta will be 0, but cos theta will be 1, which is its maximum value. And when theta is equal to pi by 2, then sine theta is 1, but cos theta is 0. Okay. So there is a basic difference in these two representations. Actually, you can see that if displacement is 0 at a position, there the pressure change will be maximum, because when sine function here will be 0, cosine function will be maximum. So there is a phase difference between these two waves of pi by 2. It means you know this cos theta may be written as sine theta plus pi by 2 or minus pi by 2. Okay. So the phase of these two waves differ from one another by pi by 2, and therefore when displacement will be maximum, then pressure will be minimum, and when displacement is minimum, then pressure will be maximum. Actually, this fact I have shown graphically here. You can see that I have plotted here psi in against of x if you keep the time constant, or you may plot it in against of t if you keep x equal to constant. Okay. This first curve represents the variation of psi and the second curve represents the variation of p. Since this psi is in terms of sine function, so at this position x equal to 0 and let us take t is equal to 0. You keep this t as fixed at 0 value. Then at this position displacement is 0, but at the same position you can see when omega t minus kx, this will be equal to 0, sine function is 0. But at the same time cosine function will be maximum and therefore p will be equal to p naught. So when psi is 0, p is maximum at p naught value. But when at this moment or at this position you can see psi is maximum at its value a, then you can see corresponding to that point here the pressure is 0. Okay. Now here at this position you can see the displacement is 0 but pressure is maximum. At this position again you can see the displacement is maximum in negative side and here pressure is 0. So you can say that pressure wave differs in phase by pi by 2 from the displacement wave. Actually this fact I have told you in my previous video while discussing the stationary wave, okay, but we have not an idea during that period regarding this fact. Now it is clear to you, okay. So this is a very important fact. Now let us see how the displacement amplitude and the pressure amplitude are related to one another. Actually this relation will be utilized when we will discuss the intensity of wave. You will find its application there. You have just seen that the pressure amplitude P naught is equal to 8bk. Here A you know is displacement amplitude and B is the bulk modulus of elasticity and K is wave vector or wave number, you know. You have learnt earlier that actually the wave velocity V, this is a square root of B over rho. While discussing the videos on continuous media, this result has come several times. So you know wave velocity or phase velocity, this is a square root of B over rho, where rho is the density of the medium and B is bulk modulus of elasticity of the medium. And that's why from this relation you can say B is equal to rho V square. So when you will replace this B in this relation, then P naught will be equal to AK rho V square. Okay. Again you know this wave velocity V is equal to omega over K, and that's why K is equal to omega by V. So if you will replace K by this omega by V, your result will be P naught equal to rho V A omega. So these are the different relations between the pressure amplitude P naught and the displacement amplitude A. Okay. Now I have told you in the beginning of my this lecture that a longitudinal wave traveling in a fluid, for example sound wave traveling in air, has actually two representations, displacement representation and pressure representation. But which representation is superior, which is more appropriate if you are, particularly if you are talking about the sound wave, okay? So you should note that the pressure representation of sound wave is more appropriate representation. The reason is that most of the detector or sensor of sound wave, for example our ear, that is human ear, or mic or electronic detector, most of these detectors detect the pressure variation. They give response to pressure variation, not displacement variation. And that's why in practical sense the pressure representation of sound wave will be superior than that its displacement representation. So I have mentioned that as sound sensors or detectors, for example, human ear or mic or electronic detector, you can say, detect pressure changes. So the description of sound as a pressure wave is preferred over the displacement wave. But how we can say that the human ear or an electronic detector give response or detect the pressure change, pressure variation, not the displacement change or displacement. For illustrating this, let us see here. In fact, displacement, you have learnt that displacement is zero where the pressure change is maximum, and the displacement is maximum where pressure change is zero. You have just seen. Actually, these are the two different. These two descriptions are actually of two different on different footings. In fact, as I have told you that a human ear or an electronic detector responds the change in pressure and not the displacement in a straightforward way. Actually, to explain this, let us consider we take two audio speakers as you can see in this figure. This one represents the one audio speaker, to each another audio speaker. And we also consider that these two audio speakers are driven by the same amplifier. It means they will produce sound of same quality, same intensity, same amplitude, everything will be same because both are driven by same amplifier. Okay. And these two audio speakers you can see in this figure have been placed in such a manner that they face each other. Okay. Now let us place a detector. This is just a human ear or you can say or any electronic detector just in the midway of these two speakers. Okay. Just in midway. It means the distance of this detector from first speaker is A, then its distance from the second speaker is also A. So that the intensity of the wave at the position of detector produced by both speakers will be same. Okay. Now the displacement of the air particles near the detector will be zero as the two sources drive these particles in opposite direction. So if you consider here is a particle of the medium, this particle is driven by the first speaker in rightward direction, and the same particle will be driven by the second speaker in leftward direction. But as they produce same waves of same intensity, so the displacement suffered by this particle due to the first wave and due to the second wave will be equal in magnitude but opposite in direction. And you know displacement is a vector quantity, so if you consider that the first wave provides a displacement x1, second provides a displacement minus x2, that will be equal to 0 because x mod of x1 will be equal to mod of minus x2 because both speakers have been driven by the same amplifier, so they will provide same displacement but in opposite direction. Now if displacement is 0, okay, displacement is 0, it means this particle will remain permanently at rest, that will not vibrate. It means the particle will not respond the wave. So the net effect of the two waves detected by the detector will be 0. It means if you put a human ear here, that human ear will hear no sound. Okay. But in practice, if we stand between two speakers, we always hear more sound. Okay, so you can say that both send compression wave and rarefaction waves together. As a result, the pressure increases at the detector. Okay, at this point, pressure is a scalar quantity, so pressure will get added, and so pressure at this same position will increase. And it means when you say that pressure increases, it means you can say that the pressure amplitude will be just doubled. If the pressure amplitude of the wave provided by the first speaker is P naught 1, and that due to a second is P naught 2, then the resultant pressure amplitude after superposition of the two wave will be the sum of P naught 1 plus P naught 2. Okay, not minus. But magnitude of this P naught 1 and P naught 2 will be equal because both speakers are identical and both are driven by the same amplifier. So this will be simply 2 P naught 1. So displacement is 0, and therefore the amplitude of the resultant amplitude here will be also 0. Resultant amplitude means displacement amplitude. But the resultant pressure amplitude is just 2 times of the amplitude of the wave from one of the speakers. Okay. So you can say that a detector detects maximum intensity in such a condition. So you can say the description in terms of pressure wave is more appropriate than the description in terms of displacement wave as far as sound properties are concerned. Okay. So I think now it is very clear to you that the displacement representation of sound wave is practically not appropriate. Practically, its pressure representation is appropriate. Okay. So I think this was a very elementary video, but the idea which we have learnt in this video, that will be used at several places when you will study the organ pipe. Then you will see that at a displacement node there will be a pressure antinode, and at the displacement antinode there will be pressure node. This is all due to this. Okay. So this idea will help you in understanding the wave concept in my forthcoming videos. Okay. Thank you very much.